Good afternoon, everyone. I welcome you all to the week 2 for the problem solving session for the NPTEL course CFD. So, we'll start the session now. So, this is the NPTEL course problem solving session for the course. So, where we interact lively to solve few assignment problems related to that week's syllabus course. So, the course instructor for this computational fluid dynamics course in NPTEL is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras. And I am Ainkara Kartiga, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So I'll be handling this session from every week, mostly on Saturdays, 3 p.m. to 5 p.m. So we'll start. So this one we have seen in the last class itself, what is the course layout and how it is covered in the classes. So this week's it is about we have in the first week we have covered the introduction to CFD and calculation of flow in a rectangular attack, while the week 2 course is about calculation of fully developed flow in a triangular attack. So the problems are almost based on the same concept. So now the books and references, this also we have seen in the last class itself. What are the books and that can be used for this particular course? So it is Computational Methods for Fluid Dynamics by Fraser and Numerical Computation of Internal and External Flows by Hirsch and Numerical Heat Transfer and Fluid Flow Hemisphere by Patankar SP and an Introduction to Computational Fluid Dynamics Finite Volume Method and Versti. And lastly, it is Computational Fluid Dynamics Basics with Application by Anderson JD. So we'll now go into this week's few problems which will be helping you in solving assignments and submission of the assignments. So yeah, in question 1, it is asked that when Mach number is greater than 0.3, the flow is option A, it is incompressible, option B, it is compressible, option C, either compressible or incompressible, option D, none of the above. So Mach number, if it is greater than above, what is it? The flow is whether compressible or incompressible is the question, and the answer to this is it is compressible flow. So we'll see what is Mach number. Mach number is nothing but it is the ratio of local flow velocity to the speed of sound in that medium. So based on this number, how we are classifying the flow is considered as compressible or incompressible is that if it is Mach number is greater than 0.3, then it is compressible flow, while in the other case if it is less than 0.3, it is incompressible flows. And in the cases when it is greater than 0.3, we have further classification as, like, if it is 1, it is transonic flows, if it is greater than 1, it is supersonic flows, and if it is less than 1, it is subsonic flows. And if it is very higher, that is if it is very much higher than 5, it is hypersonic flows. So based on the Mach number, we classify the flow into various types. In base, if it is greater than 0.3, all this comes under the compressible flows. And next question, we'll move to next question. In question 2, it is asked that Euler equation is useful for option A, viscid flow, option B, inviscid flow, option C, it is rotational flow, option D, it is none of the above. So Euler's equation, we know it is applicable for inviscid flow. So basically, for solving the fluid flow dynamics, we use the Navier-Stokes equation, where the Navier-Stokes equation is given in this form, that is rho times of dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to rho gx, that is this is momentum balance equation. So we take into account all the forces acting on the particle like pressure force, gravitational force and viscous force. So this is rho gx minus dou p by dou x plus mu times dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So we all would have seen the simplification of Navier-Stokes equation under a certain condition where viscosity is not taken into account, that we call as Euler's equation. So this term would be accounted as 0. So what we would be left with is we would be left with rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to rho gx minus dou p by dou x. That is, this term is completely gone. So this is known as Euler's equation. So in this particular case, we have neglected the effect of viscosity. So the answer to this is Euler's equation is useful for inviscid flow, that is the non-viscous flow. I hope it is clear. Now we'll go to question 3. In question 3, actually first 10 questions also are just basic concept. Afterwards we'll see problems related to this week. So in question 3 it is asked that the fluid flow with no energy loss is option A viscous flow, option B non-viscous flow, option C either viscous or non-viscous, option D none of the above. So if there is viscous flow, we all know that there will be energy loss due to transmission from one layer of the fluid to the another layer. So when there is no energy loss, when that would be the case is that non-viscous flow. So basically fluid with zero viscosity, we consider it as inviscid flows, and like this is known as no shear stress. There would be no shear stress because there is no viscosity and there is no resistance to deformation, and hence there is no energy loss due to internal friction. So if there is no viscosity, there is no resistance to fluid has no resistance to deformation, and it has no energy loss due to internal friction. And so it is like there would be no shear stress and there would be no, I mean, since it is a non-viscous flow, we have no energy loss due to internal friction. This is what is asked in the question. Fluid flow with no energy loss is non-viscous flow. There is no viscosity in the flow. Effect is no viscosity effect in the flow. So fluid flow with no energy loss is non-viscous flow. So since there is no internal energy loss due to internal friction, it is reversible flows. So we'll go to question 4. In question 4, it is asked that Navier-Stokes equation is, it is for viscous flow. Navier-Stokes equation is useful in the analysis of viscous flow, non-viscous flow, turbulent flow, and none of the above. So similar to the previous question, it is very much used in viscous flow studies. If it is non-viscous, we have seen it is as Euler's equation, where viscosity effect is neglected. So since it is included in the Navier-Stokes equation, we use it to study the viscous fluid flow. So this is the Navier-Stokes equation, rho gx minus dou p by dou x plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square is equal to rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. As we all know, this is the only I have written for one component, that is x component alone I have written. Similarly, it comes for y component as well as the z component. Navier-Stokes equation, while solving the fluid flow dynamics, we mostly have the continuity equation and three momentum conservation equation in three directions for the three u, v, w and velocity components. So four equations would be coming in picture while we are solving the CFD equations. So this is for one component only. Similarly, two other components equation will also be coming into picture. So we'll go to question 5. In question 5, the fluid in which resistance to flow takes place is viscous fluid, non-viscous fluid, either viscous or non-viscous, none of the above. So we all know that if there is a resistance to flow which is taking place, that is because of the viscosity effect. So it is for the viscous flow. Viscosity, it's nothing but it is a measure of internal friction in a fluid where it is resisting the fluid motion. And in question 6, we have when a direct computation of a dependent variable can be made in terms of known quantities, the computation is said to be option A implicit, option B explicit, option C unique, option D dependent. So as we have seen, we have a domain where we discretize the domain into small segments or small cells. So we will be having equations for all those cells and for those grids. So while solving how so consider this as our flow domain, a rectangular flow domain. So we have discretized into small grids. So we will be having equations in each of these points. So we for in order for us to solve, we have boundary conditions, and apart from that, consider we have the variables in these things. So if we have to compute time to time also, right? So the variables would be unknown at every time. So yeah, this is our domain of flow. So we have discretized into smaller grids. So we need to solve the unknowns in these grids. So what happens is that fluid will be flowing continuously. We may say that initially it is at rest. So we know the initial condition, and afterwards it will be starting to move at some velocity. So we know the velocity near the walls also. Like we can apply some conditions like no slip conditions also. So we know the boundary conditions too. But in internal things, we do not know the values of the variables at these points, everything. So we need to solve for them. So there are two ways in which we can go about this getting the solution: implicit method and explicit method. So these are all just a way of numerical approach where we will be using. This would have been covered in numerical methods itself. So in explicit method, what we would be doing is we would be solving the equation directly, whereas in implicit method we would be using the variables at the next time step to get the equation, so that all those equations would be solved simultaneously. So simultaneous solution of the equations would be done in implicit, and in explicit we would be giving you using the particular time step and would be solving the values. So what is explicit method? It is the direct calculation of the dependent variable from known values of independent variables, calculates future condition from information about the present condition of a system. So we will be getting the values at the next time step from the information we have from the present condition. Whereas in implicit method, the calculation of dependent variables on the basis of known variables from the present as well as the future. So this is the difference between explicit and implicit methods. So I have actually given a reference also which you can use to go through if you have further doubts. So basically in this question it is asked when a direct computation of the dependent variables can be made in terms of known quantities. Computation is said to be implicit, explicit, unique or dependent. Explicit is the right answer because we are using all the known quantities. So whereas in implicit method, which is another approach, we will be using the future condition as well, and solving the equation simultaneously. So implicit and explicit. Implicit would be computationally little expensive because we would be solving those equations simultaneously. So for that we need to know like proper thing to do, whereas explicit it is also easier, and so the accuracy would be depending on according to that. So we'll go to question 7. In question 7, it is asked that the for formula of forward differencing is delta h f of x is equal to f of x plus h minus f of x, or option B, it is 2 times delta h into f of x is equal to f of x plus h minus f of x minus h. Option C, it is delta h into f of x is equal to f of x minus f of x plus h. Option D, it is f of x into delta h is equal to f of x plus h plus f of x minus h. So consider this, we are solving it in a domain. So this difference between grid size is known as delta h, and this is x I, this is x I plus 1, and this is xi minus 1. So how would we get the formula for forward differencing is that in forward differencing we will be using the next value and the present value. So it is f of x plus xi plus 1 minus f of xi by delta x, or here in this case it is f of x plus h minus f of x by delta h. F of x is equal to if we take this delta h into that side, we can get f of x is equal to f of x plus h minus f of x by delta h. Whereas in option B, it is 2 times of delta h into f of x is equal to f of x plus h minus f of x minus h. This is similar to central differencing. Whereas in option C, it is delta h into f of x is equal to f of x minus f of x plus h. And option D, it is delta h into f of x is equal to f of x plus h plus f of x minus h. So option A is the right answer, where delta h into f of x is equal to f of x plus h minus f of x. That is, okay, we are taking f of x plus h minus f of x divided by this delta h would give us f of x. So if we are going with the backward differencing, we would be having f of x I minus f of xi minus 1. So that is the formula for backward differencing. So we'll go to question 8. In question 8, it is asked that the ratio between the longest side and the shortest side of the mesh is called, option A, it is mesh orthogonality, option B, it is skewness, mesh skewness, option C, it is mesh aspect ratio, option D, it is mesh smoothness. So what is asked in the question? It is asked that what is the ratio between the longest side and the shortest side of the mesh is called. So if it is, and in general, ratio between the longest side and the shortest side is called as aspect ratio. Similarly, in this case also, mesh aspect ratio is the answer, which is the ratio between the longest side and the shortest side of the mesh. So what are the other terms denote here? So we have given here, in which it is that mesh orthogonality. It is the angular deviation of the vector from a vector connecting two cell centers. So if there is two cells, like there would be like two, vector would be connecting two cell centers, and the vector deviation from this angular deviation of this vector from a vector containing two cell centers is denoted by mesh orthogonality. And in mesh skewness, it is the deviation of the vector that connect two cells from the face center. So this face center, from there we deviation of the vector that connects two cells. Whereas mesh aspect ratio, it is the ratio between the longest side and the shortest side. And mesh smoothness, it is the uniformity. I mean, it is also known as expansion rate, growth factor, uniformity. Defines a transition in size between contiguous cells. So for example, we have a cells, so it is divided like this. So as we can see that cell size is increasing in the next subsequent cells. So how smooth it is, or growth factor or the expansion ratio denotes the transition in size from one cell to another. So that is known as mesh smoothness. Whereas in the question it is asked that what is the ratio between the longest side and the shortest side of the mesh is called, it is called as aspect ratio. Like for example, if it is some cells would be like this, and if it is like this, it would be a aspect ratio. If both of them are equal, longest side and the shortest side is equal, we can say it is 1. Generally it is preferred to be closer to 1 for the mesh aspect ratio. But if entirely depends on the geometry in which we are dealing with, and how we are able to discretize or mesh the particular geometry. So that is the answer. Now we'll go to question 9. In question 9, it is asked that which of these features of structured grids is a disadvantage? Option A, it is easy to solve. Option B, it is suitable for simple geometries. Option C, efficient in memory requirements. Option D, less time requirement. So structured grids is nothing but when we are meshing the geometry, we can go with structured or unstructured mesh. So it if like further solving of that particular geometry, like solving of the equations in that particular geometry, depends on the grid. Like if it is structured, it would be easier to solve. If it is not structured grids, non-structured grids are also there, but they would be little time consuming to write the equations and solve the equations. And because like if it is a simple geometry, we can go with the structured grids, but if it is a complex geometry, we need to mesh the geometry accordingly, and according to the grids shape, it would be the further solution for obtaining the further solution is complex. So which of these features of structured grids is a disadvantage? So all of these are features of a structured grid. It is easy to solve. Option B, it is suitable for simple geometries. Option C, it is sufficient in memory requirements. Option D, it is less time requirement. So easier to solve, it is an advantage factor. Whereas in option B, it is given that suitable for simple geometries. For case of complex geometries, we cannot go with structured grids. So that is a disadvantage because it is only applicable for simple geometries. Whereas in option C, it is given efficient in memory requirements. Well, that too is an advantage. Less time requirement is an advantage. So option B is the right answer. So it is given that structured grids are those in which the grid points can be ordered in a regular Cartesian grid structure. So for example, if we are discretizing this particular domain into 4 or 5 cells, so what we will be having, we can say that this is I plus 1, this is I plus 2. Similar way, we can give the indices. So structured grids are those in which grid points can be ordered in a regular Cartesian structure. That is, the points can be given indices such that the nearest neighbor points are identified by indices I plus or minus x, j plus or minus y. That is, if it is I, we can say that I plus 1. If it is j, we can say j plus 1 or j minus 1. Anything we can give the nearest neighbors the points identified by the indices. Like previous indices, if it is ij, we can give the next nearest neighbors as I plus or minus x, j plus or minus y. So these are the structured grids. Someone, I think, Okay. Okay. I heard someone willing to join, but I think okay, we'll see. So, question 10, it is under specification of the boundary conditions gives rise to solution equal to 0, no solution, a unique solution, n number of solutions. So, for example, mm we are discretizing the domain and we'll be getting a n number of equations. For solving that, we would be requiring certain number of boundary conditions. So, if there are under specification of the boundary conditions than the required, what would happen? We would be having n number of solutions. That is, the possibility of the solutions would be very large. It we can say it is zero or no solutions, because under specifications, what we are doing, we are giving the boundary conditions less than what is required. So in that case, you would be having n number of solutions. Picking out a solution from that is not possible. So it is always wiser to give a specific number of boundary conditions that is required for that solving of that particular system. So in question 11, it is a reverse of that previous question. What happens with the over specification of boundary conditions? So previous question, it was about what happens with the under specification of the boundary conditions. Whereas in this particular question, it is about what happens when we over specify the boundary conditions. So over specification leads to infinite solutions, unique solutions, unphysical solutions, no solutions. If we specify over specific boundary conditions, it would lead to unphysical solutions. That is, those solutions would not be feasible in reality. The but over specifying the number of boundary conditions would lead to such solutions. Infinite solutions are possible when it is the under specifications, whereas the case of over specification leads to unphysical solutions. That is, option C is the right answer. So these are just some introductory problems to revise up our basics. So now we'll go into the problems related to this week, and we'll see we'll solve problems related to that. So here there is a case, and few questions are followed by that case. So in case 1, it is given that the following notation is to be used where applicable. So the following notation is to be used wherever applicable. So u is the velocity vector, u, v, w are velocity components in x, y, z coordinates. P is the pressure, mu is the viscosity, nx and y are direction cosines. So what is given? U is the velocity vector. U is the velocity vector where it is having u, v and w as the velocity components in x, y and z directions. And P is the pressure, mu is the viscosity, and nx and y are direction cosines. So first we need to see how the flow domain is. So this is a flow domain that is given. So it is this is y direction and this is x direction. So the duct would be like this. So here the flow is in z direction, or here u, v and w. So these are the takeout from this particular slide. What is given is that the flow notation is to be used wherever applicable. So u is the velocity vector u, v, w. I mean velocity vector with velocity components u, v, w in x, y, z directions. So u is in x direction, v, y and w, z coordinates. So P is the pressure, mu is the viscosity, nx and y are direction cosines. So we'll see the first question. In first question, it is given that you wish to compute the steady laminar fully developed flow field through the triangular duct shown in figure 1. For this case, the governing equation is given by, given by option 1, del dot del W is equal to 0. Option 2, it is del dot del U is equal to Z constant. Option 3, it is del dot del U is equal to minus mu delta P. So what is given? We are computing the steady laminar fully developed flow field through the triangular duct. So it is given in figure 1. For this case, the governing equation is given by del dot del W is equal to 0, del dot del U is equal to constant, del dot del U is equal to minus mu times delta P. So option A, it is 1 only, option B, it is 2 only, option C, it is 3 only, option D, none of the above. So in this particular slide itself, answer is given as none of the above. We'll see how it is. So before that, we'll once again go back to the figure 1 and see, and then come back to the solution. So here, as we can see that, this is in y direction, this is x direction, and flow is in z direction. So W component velocity only comes into picture because fluid is flowing in the z direction. So we need to account the mostly the W component velocity would be only influencing. So, and the flow, because the flow is steady state fully developed flow through this particular triangular duct, and it is laminar flow. So we'll see. So first is steady laminar fully developed flow. So we have W, which velocity only remains, where W is a function of x and y. So as you remember, the flow field is this, and y, x, and this way it is W. So W is a function of y and x. And for any solution, we need to be having the continuity equation and the momentum conservation equation written. Only from that we can proceed with getting the governing equations. So initially we have continuity equations, dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. For momentum equations, we have equation with three components, u component, v component, w component. So for this u component, the equation is rho dou u by dou t, rho times of dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus rho gx plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. And for y component, we have dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to, into rho is equal to minus dou p by dou y plus rho gy plus mu dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Similarly, we have rho times of dou w by dou t plus u times dou w by dou x plus v dou w by dou y plus w dou w by dou z is equal to minus dou p by dou z plus rho gz plus mu dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So this, what happens, we have only the w component velocity, which is a function of x and y. So the remaining equations does not influence much. So we take this equation, okay, not this, the third equation for the momentum conservation equation. So what we have is that u component is a 0, v component is a 0, and w is a function of x and y, not w is not a function of z. So the first term also vanishes. So we have, and we are using a steady state, so this term also vanishes. So LHS side completely becomes 0. And in the right hand side, we have minus dou p by dou z plus rho gz plus mu dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So the thing here is, since it is a fluid through a triangular duct, the gravity, momentum variation due to gravity is very less. So this effect is neglected as an assumption. So what we are left with, minus dou p by dou z plus mu dou square w by dou square dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. Again, this term actually vanishes because w is a function of x and y, not w is not a function of x. So we are left with dou square w by dou x square plus dou square w by dou y square into mu is equal to minus dou p by dou z. Okay, this won't come. So if we take the values to the other side, we have dou square w by dou x square plus dou square w by dou y square is equal to dou p by dou z by into 1 by mu. So if we take this, which is matching actually, del dot del w is equal to 0, or del dot del w is equal to minus dou p by dou z into 1 by mu. That is the answer. Where if we have del dot del w is equal to minus mu del p is the right answer. So, but what is given? It is given as 0. So, this is not the right answer. And del dot del u is a constant. Again, this is not right. And in option 3, it is given del dot del u is equal to minus mu by del p, but it should have been w. So, option 3 is also wrong. So, option A, option 1, 2 and 3, all 3 are wrong. And option D is the right answer. That is, none of the above is the right answer. So what we have done, we have taken the rectangular duct and given the equations in x, y, z and momentum conservation equations, and we have reduced those equations, and we found that none of the equations are matching with the given options. So all 3 of the options are wrong. So A, B, C and are wrong. So answer is none of the above. So I hope it is clear. Now we'll go to question 13. In question 13, it is given that you wish to compute the steady laminar fully developed flow field through the triangular duct. For this case, which of the following is an admissible governing equation? Okay. You wish to compute the steady laminar fully developed flow field through a triangular duct shown in figure 1. So for this case, which of the following is an admissible governing equations? So in the last slide, what we have obtained is equal to del dot del w is equal to minus 1 by mu dou p by dou z. So here what are the options given? Option 1, it is dou square w by dou x square plus dou square w by dou y square is equal to 10. And option 2, it is dou square u by dou x square plus dou square u by dou y square is equal to 10. Option 3, it is dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p by dou x. So on initially it can be seen that option 3 looks similar, but we have to see that sorry. It is dou p by dou x, whereas it should have been dou p by dou z. So option C 3 is wrong. And on looking option 1 and 2, 2 u velocity component does not come into picture. So option 1 is the right answer, because we can consider that pressure gradient, if it is a constant, if it would look like this. Option 1, dou square w by dou x square plus dou square w by dou y square is equal to 10. So this is an admissible form of the governing equation. So option A is the right answer, where it is 1 only is the right answer. I will go to question 14. In question 14, it is given that for a steady laminar fully developed flow field through a triangular duct shown in figure 1, which of the following equation is applicable? So okay, for a steady laminar flow fully developed flow through the triangular duct, which of the following equation is applicable? So u here is the vector, velocity vector, which has components u, v and w as given in the initial one. So as we can see that, so in momentum equations what we are having, del dot u is equal to 0. So we have, and previous case also we have seen that delta p by, del p, that is can be constant. So if we keep the pressure gradient variation as a constant, we can have like delta p is equal to constant. So for this, for question, it is asked that for steady laminar fully developed flow field through the triangular duct, which of the following equation is applicable? So option 1, it is delta p is equal to constant, which is applicable. Option 2, it is del dot u is equal to 0, which is a form of compressible uh, continuity equation. And option 3, it is del dot delta p is equal to constant. What would happen if delta p is equal to constant? Del dot delta p is equal to would become 0. It would not be constant. So the right statements are 1 and 2 only. So we'll see option A, it is given. First statement is right, which is correct. First statement is correct. On option B, it is given 1 and 2 are right, which is correct. And option 3, it is 1 and 3. Third statement, it is wrong. Option D, it is 1, 2 and 3. So again it is wrong because third statement is a false. So out of option A and B, we have B, which is the correct answer, because B has an inclusion of second statement too, whereas in option A it is absent. So in question 14, it is asked that for a steady laminar fully developed flow field through the triangular duct, which of the following equation is applicable? So we have continuity equation and momentum conservation equations. So on reducing those equations from the basis of our assumptions for this particular case, we will be having as governing equations. So from that, which of the following equation is applicable? So first one, it is pressure gradient is a constant, so delta p is equal to 0. If the pressure gradient is constant, delta p is equal to 0. Sorry, delta p, if it is a constant, delta p would be 0. It would not be constant. And second statement, del dot u is equal to 0, which is a continuity equation. So 1 and 2 statements are right, which is given by option B. So answer to this question is option B is the right answer. We'll go to question 15. In question 15, if the order of a discretized equation is k, what does it mean? So generally we denote an equation as second order, third order or fourth order, depending on the equation. So what happens is that we have an equation, like for example we have like dou u by dou t is equal to some constant time dou square u by dou x square or something. So we'll be discretizing these terms, the partial differential terms we'll be discretizing, and then we'll be having a certain discretized equations. But if you remember Taylor's equation, Taylor's method, there would be n number of terms for each of the we'll be have the possibility of getting n number of terms. So we'll be reducing it to certain level, and we'll call it that we'll denote it using second order equation, third order equation or first order equation or anything. So if we are saying it as a kth order, like instead of 1, 2 or 3, we have a denotion like kth order. If the order of a discretized equation is k, what does it mean? So option A, it is last term of the equation is k plus 1th power. Option B, it is last term of the equation is kth power. Truncation error is proportional to kth power. Truncation error is proportional to k minus 1th power. So what generally happens is that we would be discretizing the equation and we would be neglecting few terms and call it as a truncation error, because we cannot obviously solve for all those many equations, because on going those terms would be negligible, like effect of those terms would be negligible, so we call it as a truncation error. That, like, there would be so many errors which would be dealt in the further classes also. Like when we are dealing with CFD, error comes from many so like many steps, like a solution during discretization or during truncation, like we give names accordingly. So here, if it is a truncation error and if it is proportional to kth power, or if it is a truncation error which is proportional to k minus 1th power. So what do we mean by order of a discretized equation which is k? So answer to this question is truncation error is proportional to kth power. So for that we will see this uh, in question, like it is given that forward difference scheme. For example, we will take the forward difference scheme, and how we are denoting dou u by dou x at I comma j. We would be writing it as u I plus 1 comma j minus u I comma j divided by so we have forward difference scheme, that is dou u by dou x at I comma j is equal to u I plus 1 comma j minus u I comma j divided by delta x plus order of delta x, that is first order. So we'll see how we are going about this. For example, we have a Taylor series to get the f of x plus delta x. So how would we write the f of x plus delta x? So we have f of x plus delta x is equal to f of x plus dou f by dou x into delta x plus dou square f by dou x square into delta x square by 2. And similarly we would have so many terms like dou square cube by dou x, sorry, dou square dou cube f by dou x cube into delta x cube by 3 factorial, and dou to the power of 4f by dou x power 4 into delta x power 4 by 4 factorial. Like that we would be having n number of terms. So but here what we are doing, we are writing only till a certain number of terms. And similarly, like instead of f of x plus delta x, we have u I plus 1 comma j, that is u, we need to know the value of velocity u at I plus 1th term. So for that we have the values at u I plus 1. So yeah, by Taylor series, how can we write that? U I plus 1 j is equal to u I j plus dou u by dou x at I comma j into delta x plus dou square u by dou x square at I comma j into delta x square by 2, and so on. And we are neglecting the rest of the terms, because as you can see that delta x would be a very small quantity, and we are using delta x to the power of 2, delta x to the power of 3, so that terms would become negligible after a certain point. And here we are leaving out this term, that is dou u by dou x at I comma j into delta x, and we are taking all the rest of the terms to the right hand side, that is u I plus 1j minus u I comma j minus dou square u by dou x square at I comma j delta x square by 2. And here we have one delta x left, so we are dividing the entire equation by delta x. So dou u by dou x at I comma j is equal to u I plus 1j minus u I j divided by delta x minus dou square u by dou x square. Since we have divided by delta x, we have delta x by 2. So here we are getting a one equation form. So in the initially what we have seen the forward difference scheme for first order derivative, partial derivative dou u by dou x. For that we generally write it as u I plus 1j minus u I j divided by delta x plus order of delta x. So for that, how we have obtained, if we go backwise, we use Taylor series to get that u I plus 1 comma j equal to u I j plus dou u by dou x at I comma j into delta x plus dou square u by dou x square into delta x square by 2 and so on. Like we have kept this particular term alone in the left hand side and taken all other terms in the this particular term is left in one side and all other terms are taken to the other side. So we have dou u by dou x at I comma j into delta x is equal to u I plus 1 comma j minus u I comma j minus dou square u by dou x square at I comma j into delta x square by 2. So for this, if we compare with, and then we are dividing the equation by delta x to get the dou u by dou x at I comma j. If we compare this equation and this equation, what we have one more extra term, that is dou square u by dou x square into delta x by 2. So we call these, here there would be so many terms and all those terms are denoted by truncation error. So this truncation error, where we are having it as truncation error is of the order of delta x or first order. So here we are denoting it as a first order. So if truncation error terms are in the second order, we denote it as second order. Similarly, if we have central difference, if we are using central difference scheme to get the dou u by dou x at I comma j, what we would be having u I plus 1 j minus u I minus 1 comma j divided by 2 delta x actually. So what we are having, if we are using a central difference scheme, we would be having it as dou u by dou x at I comma j is equal to u I plus 1 comma j minus u I minus 1 comma j divided by 2 times of delta x. And what other terms we have neglected? We have neglected dou cube u by dou x cube into delta x square by 6. So since we have neglected all the other terms, we are denoting it as order of delta x square. So this is a second order equation. So this is a first order equation. This is a second order equation. So if coming back to the question, if the order of a discretized equation is k, what does it mean? Last term of the equation is of k plus 1th power. Option B, it is last term of the equation is of kth power. Option C, it is truncation error is proportional to kth power. Truncation error is proportional to k minus 1th power. So here what have we done? Truncation, if it is a first order equation, the truncation error is proportional to kth power. First power. Since it is a first order equation, we have truncation error which is proportional to the first order. First power or something. So if it is a second order equation, we are neglecting the truncation error from the second order. So second power or something. So truncation error is proportional to the kth power. So here truncation error is proportional to the first one. Here truncation error, we have neglected all these terms which is proportional to the second power. So if the order of a discretized equation is k, what does it mean? Truncation error is proportional to the kth power is the right answer. If it is a discretized equation of order k, its truncation error is proportional to kth power. So this is the answer for this question. And coming to question 16, it is given that which of these best define the Dirichlet boundary condition for the property phi at point B in a boundary. So for example, we have some geometry and the point here is A and it is here B and C and D. So which of these best define the Dirichlet boundary condition for the property phi at point B in a boundary? So in general, we have two different boundary conditions. The first one is Dirichlet boundary condition and the second is Newman boundary condition. In Dirichlet boundary condition, we specify the value of that variable at that point, whereas in Newman boundary condition, we specify the value of the derivative at that particular point. For example, consider we are heating the coil and we have one rectangular coil like this, and here the temperature, we know the temperature at here, and here we are heating it at some temperature. Like here, let us keep, we are heating it at 100 degrees Celsius, and here it is at room temperature. So we know the values at here and here. So what are we doing? We know the value at x is equal to 0 and x is equal to 10 meter or something. We know the values. So this is known as Dirichlet boundary conditions. Here we are specifying the value of that particular variable at that point. So if we know the temperature is 0 at here and temperature is 100 degrees Celsius at there, if we specify such boundary conditions, it is known as Dirichlet boundary conditions. And the next one is the Newman boundary condition. In Newman boundary conditions, what we would be giving out is, here we can give it, instead of giving temperature as 30, 40 something, we can give it as temperature is, instead of giving temperature as some value, we can also define the boundary condition as dou T by dou X at X is equal to 0 is this one, or dou T by dou X at X is equal to 10 is this one. So that is known as Newman boundary conditions. So so in this question, what is asked that which of these best define the Dirichlet boundary condition for the property phi at point B in a boundary? So instead of phi is a generalized property given over here like temperature. So if phi value is given at point B, how would we denote it? So like here, let us take it is point A and point B. So if phi value is given at point B, we would be denoting it as phi at B is equal to something x value or something y value, some values we would be denoting. So this is known as Dirichlet boundary conditions. So how are we denoting? Which of these best define the Dirichlet boundary conditions for the property phi at a point B? So first option, it is dou cube phi by dou x, sorry, dou cube phi by dou x cube. Option B, it is dou square phi by dou x square. Option C, it is dou phi by dou x. Option D, it is phi b. So answer is option D, because we are giving a Dirichlet boundary condition, not Newman boundary condition, to give the boundary. I mean, we are not giving the derivative. Since we are using the Dirichlet boundary condition and we are specifying the value at a point B, so we are using it as phi b. Phi b is equal to something. So we are denoting it as using option D is the right answer. And we'll go to question 17. Okay, in question 17, it is asked that the path of fluid particles cannot be tracked in option A, turbulent flow, option B, laminar flow, option C, mixed flow, option D, none of the above. So, like imagine a laminar flow where the flow would be very ordered and there would not be any chaos or something. So, we can track the fluid particles flow inside the in a laminar flow. So there like each layer of fluid, the force transmission or everything would be uniform. So in laminar flow, ordered motion of the fluid would be observed, so that fluid can be tracked in laminar motion. Whereas in turbulent flow, imagine there would be so much fluctuations in the flow and so much chaotic motion will be inside the fluid domain. So it is very difficult to track fluid particles in such cases. So option A, turbulent flow, is the right answer. Option B, laminar flow. Option C, mixed flow. Option D, none of the above, which are wrong answers, because path of fluid particles cannot be tracked in other flows. Like in laminar, if it is a laminar flow, we can go about tracking the fluid particles. Whereas in like imagine if it is a ordered motion, like in laminar flow, like pipe flow itself we'll consider, like motion would be like this. I mean, consider it as uniform flow, I mean uniform laminar flow. We can track the motion of the individual particles, whereas in turbulent flow the flow would be like, it would be like so much should be happening. So it becomes impossible to track the individual, I mean, fluid particles inside the domain. So answer to this particular question is option A, that is turbulent flow is the right answer. We'll go to question 18. Okay, before going to question 18, it is a case study problem similar to what we have seen in like before 5 questions. We have seen, we have taken one case and we have solved. So this is similar to that case 2. We are now going to solve by considering this particular domain. So before that, let us take a 5 minutes break. Now the time is 4:05. We'll come back shortly in 5 minutes. So, and then we'll continue the session. Okay, now we'll get back to the session. So, yeah. So, in this question, it is like similar to what we have seen previously. There, here we have a flow through a triangular duct and flow through a elliptical duct. So again, we'll see it is in YZ domain and here it is in XY domain. So just have a brief picture of it. So here we have flow through two different domains. One is a triangular duct and another one is an elliptical duct. So we'll see what questions can be asked from this case 2. So in case 1 we have seen a flow through a triangular duct only. So similar to this is the figure 1 from case 2, and additionally we have one more elliptical duct. Um, so in question 18, we'll see what question 18 is. In question 18, with respect to figure 1, for the given coordinate system, the governing equation describing steady laminar flow through the triangular duct is given by mu dou square u by dou x square plus dou square u by dou y square is equal to minus delta, minus dp by dz. B mu dou square w by dou x square plus dou square w by dou w, sorry, dou square w by dou y square is equal to minus dp by dx. And here it is mu dou square u by dou y square plus dou square u by dou z square is equal to minus dp by dx. And here it is mu dou square v by dou y square plus dou square w by dou z square is equal to minus dp by dx. So here we need to see what is given in the question. Here it is given steady laminar flow through the triangular duct. Here it is not a fully developed flow, so pressure is a pressure gradient is not a constant. So in options, in first we'll go to case 2. Here it is given that flow is through a triangular duct and we have y here and z here. So flow is in the x direction. So if we have u, v and w component, what would be the only component? So we should be dealing with u component velocity because the triangular duct is yz plane and the flow is in x direction. So here u component of velocity remains, and so we need to consider the if we look back at the equation. So here we have u component rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus rho gx plus mu dou square u by dou x square plus mu dou square u by dou y square plus dou square u by dou z square is left. So steady flow, so dou u by dou t is dou u by dou t would be 0, and here u is a function of so it is in y and z, so u is a function of y and z. So dou u by dou x is 0 and dou u by v component is 0, w component is 0, and this term remains, and gravitational effect we have neglected, and mu dou square u by dou x square plus dou square u by dou y square and dou square u by dou z square. Out of that, u is not a function of x, so this term alone goes to 0. So what we would be, sorry, left with mu dou square u by dou y square and dou square u by dou z square is equal to minus dou p by dou x. Right. If we are looking at option A, it is mu dou square u by dou x square plus dou square u by dou y square is equal to minus dp by dz. It is not dz, it should have been dx. So option A is wrong. And option B, it is mu dou square w by dou x square plus dou square w by dou y square is equal to minus dp by dx. Again, this is wrong because we are not dealing with flow in a w direction because the plane is yz plane and flow is in x direction. So again, option B is wrong. Option C, it is given dou square u by dou y square plus dou square u by dou z square is equal to minus dp by dx. This is right because here we are dealing with u is a function of y and z, so this term is right, and we are dealing with the x direction flow, so minus dp by dx is again right. So option C is the right answer. Mu dou square u by dou y square plus dou square u by dou z square is equal to minus dp by dx. So what we'll see what option D is. In option D, it is given that mu dou square v by dou y square plus dou square w by dou square z is equal dou z square is equal to minus dp by dx. Here, if we look again, everything is false because although it is in y x direction, these two terms are not right because v and w are already 0. So this term is like, so here if we look at u is a function of y and z, so this term is false, and p is not a function of z, so this is false. And here option B, it is w is component velocity is 0, and in option C it is the right one. Option D, it is v and w both velocity components are 0. So option C is the right answer, which is mu into dou square u by dou y square plus dou square u by dou z square is equal to minus dp by dx. So option 18, sorry, question 18 answer is option C. We'll go to question 19. In question 19, it is asked that steady fully developed flow through the duct represents a balance between which of the following forces. So option 1, it is inertial force. Option 2, it is viscous force. Option 3, it is pressure force. So if we are writing a Navier-Stokes equations, the forces that comes into picture would be here itself we can see that which are the forces that we are accounting here. We are accounting only the viscous force and the pressure force. Rest all forces we have neglected through some assumptions or something. So remaining what we have left with is pressure force and the viscous force viscous force. So in question 19, the answer to this problem is steady fully developed flow through a rectangular duct shown in figure 1 represents a balance between which of the following forces. So option 1, it is inertial force. Option 2, it is viscous force. Option 3, it is pressure forces. So we'll see what are all the combination of these statements are given in the answer options. So it is option A 1 and 2, 1 is false. So option A is false. Again, option B, it is 2 and 3. 2 and 3 is right because we are balancing between viscous force and pressure force. So steady fully developed flow through the triangular duct in figure 1 represents the balance between which of the following forces. It is viscous forces and pressure forces. And coming back to option C, it is 1 and 3. Since 1 is there, it is false. And again in option D, it is 1, 2 and 3. So again, because of 1, it is a false statement. So steady fully developed flow through the triangular duct represents the balance between viscous force and pressure force. That is option B is the right answer, which we can see from the governing balance from the equations. Governing equations we have written and we have arrived at these equations. So it is mu dou square u by dou y square plus mu dou square u by dou z square is equal to minus dp by dx. So we are accounting viscous force and the pressure force. So similar concept is this question is an extension of question 18. So we are accounting viscous force and pressure force, which is option B. And we'll go to question 20. In question 20, it is given that the vector form of the governing equation for flow through ellipsoidal duct is shown in figure 2 is the vector form of the governing equation for flow through ellipsoidal duct in figure 2 is, so we'll see ellipsoidal duct. So this is a figure 2 where we are seeing flow through a ellipsoidal duct, and if we look at, we are dealing with flow between, this is x direction and this is y direction, and the duct would be like this. So it is in z direction. So the flow is through a ellipsoidal duct. Uh, the ellipsoidal is in plane y and x, and the flow is in the z direction. So xy plane is the ellipsoid. Cross section, if we take the cross section of the ellipsoidal duct, it is in xy plane, and the flow is through z direction. So we'll go to question 20, I guess. Yeah. In question 20, it is asked that the vector form of the governing equation for flow through ellipsoidal duct is shown in figure 2. So the flow, as we can see, it is in z direction. And so what velocity remains? We have w component velocity. Okay, w component where it is a function of x and y. So, okay, in question itself, what they have asked is vector form of the governing equation. So, instead of writing it in the u, v or w component, we need to give it in the vector component. So, here the flow vector is u, and which is having the components u, v and w. So, in order to write the vector form of the governing equations, first we need to write the governing equation in the so rho, I mean in left hand side, if we go with the momentum equation, if this is component wise we have written, so instead of that, if we are taking the vector form, what we have is minus delta p plus rho g we have neglected, and this mu del dot delta u is the only term that is left. So this term, obviously because of steady state and the continuity equation, all these become 0 in the left hand side. So delta P and the viscous force alone remains. So U is the velocity vector is given. So in this question it is not asked to write the governing equation in terms of U, V or W component of the velocity. Rather it is asked to write it in the vector form. So option A, it is given as mu del dot delta u is equal to minus dp by dx, and option B, it is mu del dot delta v is equal to minus dp by dy, and C, it is mu del dot delta w is equal to minus dp by dz, and it is mu del square u is equal to minus del p. So here in option A, B and C, what equations are those is that those are the equations, but they are in the component velocity component form. So it is the x component momentum equation, y component momentum equation and the z component momentum equation. But in question 20, it is rather asked to write the governing equation in terms of the vector form, comprising both, all three u, v and w. So even though it can be written in A, B, C forms, and more specifically in the C form because it is flowing in the Z plane, Z direction, those are not the answers. Rather, option D is the right answer because mu del square u is equal to minus delta p, where u is the velocity vector. Because the question is about writing the governing equation in terms of the vector form, the option D is the right answer. If it is a question regarding anything else, governing equation, simple governing equation, the option C would have been more accurate. But in question, it is asked to write the vector form of the governing equations. So this is the Navier-Stokes equation in vector form, where we have neglected the because where we have applied the assumptions like steady state flow and like gravitational force and all, it has been neglected due to not much impact. So mu del square u is equal to minus delta p is the right answer. Option D is the right answer. Now we'll go to question 20 answer. Okay. The sorry. Continuity equation is del dot u is equal to 0. Momentum equation is rho dou u by dou t plus mu u dot del u is equal to 0, and minus delta p plus rho g is plus mu del dot delta u. So these terms become 0, and again we have neglected this, so this term alone remains. So that is what is given in option D. Mu del square u is equal to minus delta p, where u is the velocity vector. Okay, I heard someone was joining. Okay, no issues. We'll go to next question. Hmm. Okay, question 21. Which method would you use to solve for the velocity field in the ellipsoidal duct if you wish to solve in the xy coordinate system? Which method would you use to solve for the velocity field in the ellipsoidal duct if you wish to solve in the xy coordinate system? Given things are finite volume method. Option say 2, it is finite difference method. Option 3, it is finite element method. So if we are dealing with solving the velocity field in the ellipsoidal duct, if you wish to solve in the xy coordinate system, what would be using? It is finite volume method, finite difference method, or finite element method. So options are option 1 only, option 2 only, option 1 and 3, and option D, it is 2 and 3. For example, the duct is like this. So if we are willing to use the xy coordinate system, we are using in the Cartesian coordinate system. So here finite difference approach is not possible. Finite difference approach is not possible because in finite volume method we would be dividing the geometry or domain into a small volume. Similar thing is applicable in the finite element method, where individual elements are divided. Rather, in finite difference method, as we have seen, we would be jumping from one position to the other, which case discretization of this particular domain is not possible in the xy coordinate system. If we change the coordinate system, we can use like r theta z and then and so on. So but in xy coordinate system, it is not possible to use the finite difference approach, and so options 1 and 3 are the only right statement. So the from picking the option from the given choices, A, it is only 1, and B, it is only 2, and option C, it is 1 and 3, option D, it is 2 and 3. So on looking at it, we can say that it is option A, it is finite element method, it is right. Option 2, it is wrong. Option C, it is 1 and 3 is right. Option C, 2 and 3, because of 2 it is not right. Because in the question it is clearly mentioned that would be solving for the velocity field in the ellipsoidal duct in the xy coordinate system, which is not possible in the finite difference approach. So finite volume approach and finite element approach is the right answers. So 1 and 3, which is given from the option C. So C is the right answer. I hope it is clear. Now we'll go to question 22. In question 22, it is asked that for the domain in figure 1, if the velocity field is specified to be, if the wall velocity is specified to be 0, how many algebraic equations would need to be solved? Option A, it is 6. Option B, it is 7. Option 3, it is 13. Option D, it is 16. So I guess we can just pick out that particular figure and put it over here so that it will be easy for us to count. So for the domain in figure 1, this is the figure 1. If the wall velocity is specified to be 0, so we are applying wall in any other walls, the velocity is 0. So velocity at this walls is 0, and this wall is 0. How many algebraic equations would need to be solved? So here how many cells we are having? Here we are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 number of cells we are having. So if we since it is a rectangular domain, we can go with the finite volume approach, where instead of taking the cell, the points, the walls or so, we would be taking the values at the cell centers, right? So in finite volume approach, if you can remember, we would be solving at the cell centers. So here we would be writing equations based on the cell centers. So based on that, we would be having 16 cell centers. 1, 2, here 1, 2, 3, 4, 5. Similarly we have for 16 cells. Right. So we need values at algebra. We will be having for the equation for the 16 cells. And these boundary conditions can be applied, but it will not be reducing the number of equations. So for the domain shown in figure 1, if the wall velocity is specified, wall velocity is specified to be 0. We are applying it as a boundary condition. But apart from that, how many algebraic equations we would be needing to solve? How many algebraic equations would need to be solved? We have 16 cells, so 16 equations needs to be solved. So option D is the right answer. Option A it is 6, option B it is 7, 13 and 16. It is all these are false. All the option A, B and C are false. Option D is the right answer. 16 equations needs to be solved. So this is the last problem for this session. So if you have any doubts, you can ask. We'll leave 5 minutes for the session. Question and answer. If not, we'll just have a quick recap of today's session and then we can propose the session. If you have any doubts in any of the problems, you can ask. Like in the assignment problems, mostly for the triangular duct, it would be application based question as I remember. So you just need to solve similar to what is taught in the lecture. So on the basis of that application, if you put the equations on the solving, the answer can be found. So this answer to these problems can be solved in the next week session, like because since it is an assignment submission, I guess the assignment submission date is 7th. Please check again. I'm not really sure, but in assignments 2 I think the deadline is 7th or so. So once the deadline is crossed, we can discuss the answers for those questions as well. Before that it is not possible. So like similar to what is taught in sir's lecture, like in those 5 modules, if you attempt to solve it, it can be solvable. Like these are just, in today's problems, I guess it is like just giving an very overview, because finding similar problems are difficult, which can be rectified from the next class as well. That's it. Like mostly what we would be dealing with is, if whatever domain we have, the first thing is we would be discretizing the domain. For that we use 3 approaches, like finite difference approach, finite volume approach and finite element approach. So in finite difference method was seen in the last rectangular duct problem, and in this it is about finite volume method for the triangular duct. So after discretization, the entire geometry is divided into smaller grids. So for those grids, we write the governing equations would be discretized, and the partial differential equation, which was the initial case in the continuity equation or the momentum conservation equation, is now converted into the algebraic equations. So these algebraic equations in these cells can be solved using the numerical methods. So there are like various methods, like you can either solve explicitly or implicitly by using various techniques like Gauss-Seidel approach and Thomas algorithm. There are so many algorithms. These are for basic approaches. So this can be used to get the values. So you will be getting discrete values for the velocity fields or something. And I mean those discrete values are the answers for the problems. So that is the thing we would be doing if in CFD as a overview. So like and the further of processing, like we have three stages: pre-processing, solution, and post-processing. In pre-processing we would be creating the geometry and meshing, and in solving we use various techniques to solve the algebraic equations which we have obtained after the meshing. Like after meshing we would be using the partial differential equation converting the partial differential equation into the algebraic equation and using various methods to solve. And in post processing we would be using various visualization tools, or we would be post processing those results to according to what we need. That would be done in the post processing. So these are the, I mean this are just overview. So if you have any doubts you can ask. Okay, if there is no doubts, I'll just give an overview of what we saw in today's class and then we can close. Mm. So this week it is about calculation of fully developed flow in a triangular duct. And here in first 10 or so problems we just saw and just to like basics of the concepts, fluid mechanics mostly. So first question, Mach number greater than 0.3, it was compressible flows. And Euler's equation for inviscid flows, and how from the Navier-Stokes equation, if we neglect the effect of viscosity, we are getting the Euler's equation, which is an assumption in Euler's equations. So the fluid flow with no energy loss is obviously for the non-viscous flows, because viscosity there is a friction and there is energy loss which is absent in the inviscid flow. Like there is no viscosity and there is no resistance to deformation, and so like in no internal energy and no energy loss due to internal friction. And Navier-Stokes equation is used in the viscous flow, and like this is one component. Similar component can be written in y and z as well. And fluid in which resistance to flow motion takes place is viscous flow. And we have seen the difference between implicit and explicit approach, and like how in implicit we can simultaneously we would be solving the present and the future conditions, whereas in the explicit we would be solving only for the present condition. So the computational accuracy and the computational expensiveness depends on these two algorithms as well. In explicit, we calculate for future condition based on the present condition information. Whereas in implicit, we calculate the few variables based on the future and the present condition variables. So, and forward differencing we have seen, and various mesh properties, these orthogonality, skewness, aspect ratio, smoothness, everything would be looked into when we are doing the meshing. So a perfect mesh should have some criteria, like it should be passing all these tests. So based on these uh, like values, we can say the mesh is a proper mesh, or if it can be used for the further solution, or it needs to be further improved. So mesh quality index or something we can say, orthogonality, skewness, aspect ratio, smoothness, everything. So definitions are given. And for structured grids it is easier to solve, but it is used only for, it can be used for simple geometries, which is a disadvantage. And under specification leads to and more solutions, whereas over specification leads to unphysical solutions. And we saw the flow through a triangular duct, and it was about the governing equation which we obtained after reducing from the continuity and the momentum conservation equation. And it is the, similarly we have similarly we have seen for further writing of the equations, and we have seen how what is the truncation error, and if it is order of the discretized equation is k, truncation error is proportional to kth power. and like boundary conditions we have seen, and fluid particles cannot be tracked in turbulent flow. And similarly for two more ducts, like triangular ducts and ellipsoidal duct, the study has been I mean we have seen the governing equations, how it is reducing. So and then it is about finite difference and finite finite volume method and finite element method for the case of ellipsoidal duct, and it is 16 number of equations, and that's it. Thank you. So if there is any doubt you can ask, or else we can close the session. Like if there is any doubt you can post it in the chat box also, I can read and reply. Like all these lecture videos and the PPTs would be available from the NPTEL. Like they would be sharing these link as well for this separately for the problem solving sessions. So if there is any doubt, you can access them as well. So that's it for today. So I thank everyone for attending. If there is no doubts, we'll close the session by after 3 minutes. And we can have the class again. Like this problem solving session would be again on next Saturday. 3 to 5 p.m. unless until there is any change. If there is any change, you will be notified prior. Okay, thank you. I am closing the session. Thank you. Thank you everyone for attending.